Hi everyone, welcome to our first lecture of Chapter 6. Today we are going to talk about thermochemistry, which is anything in chemistry that has to do with heat. So, since we're talking about heat, we have to talk about energy. And even though chemistry is the study of matter specifically, the energy is affecting the matter. And energy we're going to define as anything that has the capacity to do work. And work is kind of a physics term that we'll use in this chapter for chemistry because there's a lot of overlap between physics and chemistry. And work is defined as a force acting over a distance. So energy can come in the form of work, which is a force acting over a distance. Heat, which is a little different from energy, is the flow of energy. Okay, so heat is what we call energy, which is in motion. So they're not the same thing. And that heat flow is caused by a difference in temperature. Okay, so it's always going to flow from a hot object to a cold object. And heat is energy in motion. So you can't have heat. You can have energy, and you can gain heat or lose heat, but you can't have heat. Okay, so that's how we're going to define those terms or use those terms differently. And that energy can be exchanged between objects through contact, and we call this thermal contact. And again, we're always going to talk about collisions when we're going to talk about chemistry. In order to have a reaction, we need to have a collision. In order to exchange energy, we need to have a collision. We need to be able to have those molecules touching in some way. So again, heat involves the transfer of energy between two objects, and this is due to a temperature difference. So it's always going to flow from a hot object to a cold object. And then work, like I said, is a force acting over a distance, and these two terms, heat and work, are going to play into our calculation for energy. And energy is what we call a state function. Okay, work and heat are not. And a state function is a property that doesn't depend on the system's past or future. So like you can have heat, my apologies. You can have energy, but you can't have heat. You can't have work. You can do work, or work can be done on a system. You can gain heat or you can lose heat, but you can't have heat, you can't have work, but you can have energy. So things that you can have like that would be a state function. So it doesn't depend on the system's past or future, it just depends on the present state. You can have it right now. Whereas when we calculate heat and work, we will look at how much did it have before, how much did it have after, okay, how much was lost or gained. Okay, so that does depend on what is happening. So here's some definitions. We have the law of conservation of energy, which states that energy cannot be created or destroyed, but it can be converted between forms. So if you lose energy, then it has to go somewhere, right? Or maybe that energy was being used to do work, right? But it has to go somewhere. It can be converted into work, it can be converted into heat, but you can't just lose it. And the first law of thermodynamics goes hand in hand with that. It's that the total energy content of the universe is constant, which is kind of a broad concept, right? When we're thinking about the entire universe, normally we're going to think about like our reaction, which we will call the system. And then we're going to think about everything else, which is called the surroundings. So let's go ahead and flip to that. So we have the system, the part of the universe on which we wish to focus. So this would be our reaction typically in chemistry. Okay, and then we have the surroundings that include everything else in the entire universe, which again is kind of broad. So most times we're going to think about this maybe as like the lab, or maybe the water that your reaction is in. Okay, so you don't have to actually go through and calculate the energy of the entire universe. We're going to look more at the immediate surroundings. Okay, so we have two different types of reactions that can occur. We have an endothermic reaction, which is where heat is flowing into a system. And that means if it's flowing into a system, right, that heat needed to come from somewhere, so that heat is being absorbed from the surroundings. And then we also have exothermic reactions, which is when heat is flowing out of a system. And again, right? That heat has to be, coming from somewhere. It has to go somewhere. So if the heat is being lost by our system, then it's being gained by our surroundings, and it will always be equal. Okay, so if it's being lost by a reaction, it's being gained by the surroundings. If it's being, gained by the surroundings, by our system, that means it was lost from the surroundings. So they go hand in hand. To keep your terms straight, endothermic versus exothermic, you can think of this one. Our system is taking in heat, and in this one, heat is exiting our system. So in that way, right, those prefixes are kind of helping you to keep them straight. Okay, so like I said, we define our system as the material or process with which we are studying, okay? So again, this is going to typically be our reaction. So anytime you can, you hear the word system, you can think about this is our reaction that we're talking about. And the surroundings as everything else that is, literally surrounding our reaction. So again, that could be the entire universe. Most times we're just going to think about it, as the water that's around our reaction, or as maybe, if heat's being lost to the lab or something like that. And in this way, like I said, energy is being conserved. It's either going from the system to the surroundings or from the surroundings to the system, but it always has to, be accounted for. Okay, so we have two different terms. We have heat, which is going to be represented by the letter Q. I know that that's a little bit strange, but the capital H is going to be taken by enthalpy, which we'll look at in a later lecture for thermo, and lowercase h is Planck's constant, which we will use when we get to quantum. So all of the h's were taken up, so Q is heat, and then work is going to be a lowercase w. And so energy is being exchanged, right? Energy is our state function, and the two ways that our energy can be exchanged is through heat and work. Okay, so heat is something that we're familiar with, right? You can heat up your coffee or whatever the case may be, right? And then work is going to be a force acting over a distance, right? So maybe, you pushed something. That would be you doing work, right? Because you're expending energy, but you didn't necessarily, heat it up. So you can either do work, or you can, gain or lose heat, and both of those will be calculated for our energy. So this is our delta E. That is our change in internal energy, which you can think of as our change in energy, and it has to do with Q and W, heat and work. Okay, so delta E is our change in internal energy of a system. And so Q can either be positive or negative, but Q is going to be heat flowing into or out of our system. If heat is leaving our system, right? If we are losing heat, then that is going to be a negative Q, right? You can think of, right? That should make sense. We're losing heat, so we are, subtracting some energy, so we get a negative Q. If we are gaining heat, then heat is entering. We're gaining energy, so that's going to be a positive Q. So work is done by or on the system, and that's usually one that people have a little bit more trouble with the sign. So just because work is kind of a new topic for us in chemistry that you may not have encountered in previous classes. So we're going to use negative work if work is being done by the system, okay? And so what I mean by the system is if, say we're talking about a gas, and our gas expands. That is work being done by our gas. Our gas has expanded. It's pushed on the piston, or it's pushed on the balloon, right? It's done work. So that's, work being done by our gas. And then we would have a positive work if work is being done on the system. So now let's take our same gas, and instead of it being expanding, right, we are going to compress our gas. We are going to squish our gas into, a CO2 cylinder. That would be work being done on the system. Okay, so you want to always, when you're thinking about work, you want to think, is my gas or is my, reaction doing the work? Is it causing the expansion, or is it being, compressed, right? Is work being done on my system? Okay, it's negative work if work is being done by the system because it is using up energy to do that work, right? And it's positive work if work is being done on the system, because you can think about, if you're squishing it in, you're increasing the energy of the system. Okay, so those are going to be our definitions here. And like I said, the tricky part here is figuring out the sign, right? Is it going to be negative Q or positive Q? Is it going to be negative work or positive work? Okay, so this is a reaction diagram, and this one is for an endothermic reaction. And this is when energy is flowing into the system. Okay, so just a little bit about reaction diagrams in general. We have our energy here on the left, and then this is like the progress of our reaction. You can think about this as being time, or just as the reaction goes. So our reactants will start with some amount of energy here, and over time, since this is an endothermic reaction, they will take in energy. So our heat of our system is increasing. Okay, so our energy of the products is higher than our energy of the reactants. Okay, and so this difference in energy between the products and the reactants, this is called delta H, or the change in enthalpy. And we'll talk more about that later. But that's just the difference between the energy of the reactants and the products. And here, we're not going to talk about this much in this class, but the difference between the energy of the reactants and the top here, the very top of our reaction, the highest energy point, that's called the activation energy. And that's the energy that you need to input into the system to make the reaction go. Okay, endothermic reactions tend to have a very high activation energy because endothermic reactions need to take in energy in order to make the reaction happen. Okay, here up at the top, so you'll notice we have a positive Q of the system, right? So if our system is taking in heat, then that means our surroundings are losing heat. And in this way, right, that total energy content of the universe is constant because the energy that's being gained by the system was lost by the surroundings. Okay, energy can't be created or destroyed. It has to come from somewhere. Okay, so when the energy is being, flowing into a system, it has to come from the surroundings. And so if our Qs, right, if we were having a positive Q for our system and our negative Q for our surroundings, and no work is being done, right, because we had delta E is equal to Q plus W. So if no work is being done, then delta E is equal to Q. So if we have, our positive Q for our system, that's our negative Q for our surroundings. And if Q is equal to delta E here, then we have, our positive delta E of our system is equal to our negative delta E of our surroundings. So that's true whenever work is not being done. Then our Q is equal to our delta E. Okay, so if energy is flowing into a system and no work is being done, then our delta E of our system is positive. And when, so that means the delta E of our system is positive, then our delta E of our surroundings is negative. They are always going to be equal and opposite because all of the energy that's being lost by our surroundings is being gained by our system. Okay, this is for an exothermic reaction now. We looked at endothermic earlier, now this is exothermic. So we're going to start with some energy of our reactants, but now in this exothermic reaction, our reactants are losing energy. So now we're going to get a negative Q of our system. Okay, so that means when we are losing energy, our energy of our products will be lower than the energy of our reactants. Okay, and again, any energy that's being lost by our system is being gained by our surroundings. We still have this delta H value here that shows the difference between the reactants and the products, right? That's going to be the difference in energy there. But you'll notice now that it is negative because our system has lost heat. Okay, so it has a negative delta H. Again, more on this delta H value later, but I do want to start introducing it now. So if it's being lost, it's going to be negative, just like our Q value. And then pointing it out, again, we're not going to talk much about activation energy in this class, but you'll notice that this exothermic reaction has a much smaller activation energy because it's not requiring so much heat to get it going. It doesn't require as much energy to start this reaction. Okay, so if energy is flowing out of our system, it has to go somewhere and it will go to the surroundings. Okay, so again, like we said before, if delta E is equal to Q plus W and we're not doing any work, then our delta E is equal to Q. So here, if our system has a negative Q, that means it's losing heat and it would have a negative delta E because Q is equal to delta E because no work's being done. So that would mean, this is a positive Q and therefore a positive delta E. So if energy is flowing out of a system and no work is being done, then our delta E of our system is negative. And since it is negative, that means our delta E for our surroundings is positive. They're always going to be equal and opposite. All of the energy lost by our system is going to be gained by our surroundings. So now we have, for gases specifically, we have work. Sorry, my signs didn't come in up there. We have work is equal to negative P times our change in volume. Okay, and so this is specifically for gases. Okay, work is equal to negative P times a change in volume. So negative pressure times a change in volume. And this pressure is going to be in ATMs. Our volume is going to be in liters. Okay, so now if we think about expansion. So our expansion, that means our change in volume is, positive, right? Because we are increasing. Our change in volume, we are always going to calculate as VF minus VI. And hopefully you can see that there. Okay, so we're always going to do final minus initial. So if we have final minus initial, and our final volume is larger, right, because it has expanded, that means we have a positive delta V. Okay, so if we have a positive delta V mathematically here, right, that means we are going to get a negative W because pressure can't be negative. So if we have a positive delta V times, we've got this negative out front here, that means our work is going to be negative. So that means our energy of the system is decreasing, right? Because if you think about delta E is equal to Q plus W. So if we have a negative work, that means our delta E of our system is going to decrease. And therefore, work has been done by the system on the surroundings. So anytime we have a positive delta V, right, we have an expansion. You can think about our gas is like pressing on our container. That means when it's pressing on the container, it's going to expand, it's doing work, right? And so to do work, it needed to use some energy to do that. So our energy of our system decreases and work has been done by the system on the surroundings. If we have a compression, which is opposite, right? Now we are squishing our gas, right? And so our final volume is going to be smaller than our initial volume. So when our final volume is smaller, we're going to have a negative delta V. Okay, because, just based on subtraction, we're going to do a smaller number minus big number. We're going to get negative delta V. And so when we get a negative delta V, mathematically here up at the top, that means we're going to get a negative for our delta V times a negative, which will cause our work to be positive. And when our work is positive, now we can plug it into this equation. And when our work is positive, that means our energy of our system will increase. Okay, and then when our energy of our system increases, we say that work has been done by, on the system by the surroundings, right? Because we compressed our gas, we squished it, right? So we have done work on our gas. So you can use these two equations to kind of think through how our work, value has changed. Okay, usually it's going to be an expansion is going to be work done by the system, and a compression is work done on the system. And then you can go through this kind of whole logic, what's happening to the change in volume, how does that affect W, how does that affect delta E, to figure all of this out. Okay, let's go ahead and try an example. This says if the burning of fuel in a potato cannon performs 855 joules of work on the potato and produces 1,422 joules of heat, what is the change in energy for the burning of the fuel? Okay, so we have our equation here, delta E, delta E is equal to Q plus W. Okay, so we have, it's performing work. So we have 855 joules of work. And the potato cannon, right, so we're looking at the burning of the fuel for our delta E. Okay, so our burning of our fuel is performing the work. The work is being done on the potato, but it's being done by the fuel. Okay, so the work is done by the fuel. So our fuel is doing work. So that means we are going to have a negative work, which means it's going to be negative 855 joules. Okay, and it's going to produce heat. It's going to release heat, right? And that should make sense when we're burning fuel, right? It gets hot. So that's going to be a negative Q. So this is negative 1,422 joules. So when we do our delta E is equal to Q plus W, that means our delta E is equal to negative 855 plus a negative 1,422, which means our delta E is negative 2,277 joules. So again, this problem isn't hard. It's just, figuring out the signs of our Q and our W. Since, the fuel is the one performing the work, it's doing the work, we got a negative W. And since it's releasing heat, right, it's producing heat, we got a negative Q. So you always need to pay attention to the wording in the problem to figure out, is this going to be a positive or a negative W? Is it a positive or a negative Q? Because that's going to change your value of delta E. Okay? And that is the end of our first set of slides for Chapter 6. So go ahead and practice those problems on the Chapter 6 lecture worksheet. Get some, work with these definitions and these new terms, and send me any questions you have. Make sure you're building a really strong foundation for thermochemistry, and I will talk to you all next time.